Yo tengo una señal. Voy a poner una señal periódica. Y esta señal está en el tiempo. Y yo voy a tomar muestras de ella. Mis muestras van a ser así. Yo voy a tomar muchas muestras. Si yo tomo muchas muestras, mi periodo, y luego vamos a marcar en negro, de aquí a aquí, este es el periodo de la señal que estoy. Vale. Si yo hago su transformada de Fourier continua. Entonces, si yo hago su transformada de Fourier continua, pues aquí tendré x de j omega, omega solo, y va omega. Entonces, este tendrá un periodo asociado. Tendrá un seno, tendrá un par de delta a omega 0 y 2 omega. Y la relación con T, ¿sabéis qué es? Esta no se te da nada.
¿Cuál es la diferencia entre un terremoto y un volcán? El terremoto es sucio y el volcán lava.
Vale, entonces, este T, que es el periodo de la señal, pues ahí tengo yo mi frecuencia fundamental, ¿no? Vale, ahora esto lo voy a muestrear, esto lo he muestreado. Cuando yo lo muestré, su transformada de Fourier, aquí vamos a poner transformada de Fourier, la transformada de Fourier la ponemos así, pero pues ahora estamos en azul, pues ahora en el mundo discreto, dando más largo, yo tengo la transformada de Fourier y este será pi, este será 2pi, y por aquí tendré menos pi. Y este es mi eje de frecuencia discreta. Acordaos siempre. ¿Esto cuáles son las unidades de la frecuencia esta? Radianes por segundo. Radianes por segundo. Y de esta, unidad del tiempo. Radianes por muestra. Radianes por muestra. Radianes por muestra. Vale. Bueno, pues, entonces, aquí lo que me aparecerán serán un par de delta. Muy bien. Y la relación entre este y este, pues será omega igual a omega partido de x. Este es el periodo de muestra. Vale, o sea que lo que ocurre aquí a omega 0, aquí ocurre omega, pero ahora discreta. Muy bien. Ahora, ¿qué pasa si yo, en vez de tomar esas muestras, yo empiezo a espaciarlas más? Por no enredar mucho en el mismo dibujo, voy a repetir, ¿vale? Entonces, tengo aquí x de t, en la misma frecuencia de antes, la misma. Y ahora, lo que pasa es que voy a tomar menos muestras. Voy a tomar muestras rojas, que están mucho más separadas de las de antes. A mi periodo t sub s' es mayor que t sub s. ¿Qué pasa? Claro, aquí no he puesto la otra copia, pero aquí hay otra copia del espectro. La copia del espectro está a esta frecuencia. Vale. ¿Este punto quién es? Este punto es 2pi menos omega 0. Vale. Bueno, ahora he tomado mis muestras rojas. Y ahora mis muestras rojas, cuando yo haga su transforma de Fourier.
¿Pero porque hay menos muestras?
Porque he puesto un periodo de muestreo más grande. ¿Vale? Vale. He puesto un periodo de muestreo más grande donde este es mi módulo, sigo utilizando las mismas letras, ¿vale? O sea, no renombro las señales, digo, esta es X1, esta es X2, nada, da igual, todas se llaman X. Ahora, ¿qué pasa? Pues que esto de aquí, ¿a ti qué te parece que es? Pues se expanden y ahora ocurre a una frecuencia más alta. Pero claro, por este lado pasa igual. Por este lado, este punto de aquí también se me expande, pero ahora va hacia la izquierda. Vale. Entonces aquí, el otro. Muy bien. Todavía no he llegado a ni. Ahora, ¿qué pasa? Vamos a hacer otro más. Ya estoy justo en nicklis. Justo en nicklis, lo que tengo son 2 muestras por ciclo. 2 muestras por ciclo que tengo. Está mi señal. Las muestras van a ser verdes. Pues tengo 2 muestras por ciclo. Tengo 1, 2 y ahora lo hago, son 2. Tengo 1, 2 y luego la siguiente que me pillaría. Vale. Vale. Y ahora su transformada de Fourier. Fijaos este seno va 1 menos 1, 1 menos 1, 1 menos 1. ¿Ese quién es? Eso es... ¿Qué frecuencia es esta? 1 menos 1, 1 menos 1. Pi. Esa es la frecuencia pi. Luego estoy en pi y tengo aquí mis 2 deltas. Y tengo 2 deltas. Tengo la de la copia esta. Fijaos lo que está pasando con esta delta. Esta delta se me pasa aquí. Aumento todavía más el periodo de muestreo. Esta se me pasa aquí. ¿Vale? Pero aquí está pasando al revés. Esta se me viene aquí. Y esta se me viene aquí. Con lo cual, ahí lo que tengo es, si yo vamos a ir poniendo números, este era el azul, pues si aquí tengo amplitudes 1 medio y 1 medio, aquí voy a tener también amplitudes 1 medio, 1 medio, pero en este ya no. En este se me junta el 1 medio que viene de aquí con el 1 medio que viene de aquí. Con lo cual ahora tengo amplitud 1. Este tiene amplitud 1 y este también. Pues se juntan también 2. Y aquí justo estoy en nicklis. Pero yo sigo, pero no, yo no habéis venido nunca a esta clase ni a la de TC2 y seguía aumentando vuestra periodo de muestreo. Entonces, aquí mi seno, y ahora me voy a quedar sin colores, no me cae mucho. Cojo uno, este sería lo mínimo que necesitaría, pero no me pasa, me he cogido este. Vale. Y el otro, pues donde toque, más allá. Siempre ponerle un dedo eje, ¿vale? Vale, ahora ¿qué pasa? Pues que mi espectro sería el negro aquí. Vale. En mi espectro va a seguir pasando el mismo de antes. Voy a seguir teniendo. A ver, ¿qué estaba pasando todo el rato? Conforme tú aumentabas tu periodo de muestreo, tu delta se iba desplazando hacia la izquierda. Pues aquí pasa lo mismo, se sigue desplazando. Lo que pasa es que ahora se pasa de aquí. O sea, esta delta se sigue desplazando, se me viene aquí. Esta tiene altura 1 medio. Esta es la que viene de aquí. La que se iba desplazando todo el rato hacia la derecha. Pero es que la que se me venía desplazando hacia la izquierda también le pasa. Y ahora, se me viene aquí. Esta es la que viene de la izquierda. Y también tiene altura 1,5. Y por este lado también. Sí, fijándose solamente en un lado del espectro. Luego, esta copia que estoy viendo aquí no es una señal que provenga de mi señal original. Es la señal que viene de mi copia. Y la de mi señal original se me ha escapado de mi rango de visión, ¿no? O sea, yo normalmente miro de menos pi a pi y eso lo voy a utilizar para reconstruir. Ahora, lo he hecho con una delta, pero ¿y si lo hago con un espectro? Pues si yo tenía un espectro, pues así originalmente, nuestro espectro original era celestial, pues si mi espectro original era así, y iba desde menos pi hasta pi, ¿vale? Tenía una frecuencia máxima aquí, omega máxima, y esto era x de e elevado a omega, y este es omega, y por aquí hay otra copia, que estaba centrada en los pi. Pues ahora lo que resulta es que después de tener aliasing, o sea, si yo muestreo por un periodo de muestreo muy bajo, pues ahora este espectro súper ancho, pasándome de pi, y este espectro también es súper ancho. Y también me pasó de pi. Con lo cual, a alta frecuencia, yo lo que veo es, hasta este punto no tengo problema, vamos a utilizar otro. Hasta este punto no tengo problema, todo esto está bien. ¿Sabes? Okay. Pero a partir de este punto, bueno, vamos a ponerlo, debería haberlo hecho. ¿Okay? Pero a partir de este punto, ¿qué pasa? Pues que se me están mezclando dos espectros. Se me está mezclando este espectro con este. Pues ese será el aliasing. A ver si encuentro alguna figura que se ve muy bien. Eso.
¿Qué es lo de la rueda?
Ahora. Llegaré a la rueda, ¿vale? Imagen. Aquí, por ejemplo, esta. Pues, esa no se ve. Esta. La señal de verdad es la roja, ¿vale? Pero yo tengo un periodo de muestra muy grande, con lo cual yo la roja nunca la veo, o sea, es la analógica. Yo lo que veo es lo que he digitalizado. Pues yo lo que veo son los puntos azules. ¿Y qué me hace esos puntos azules? Porque yo voy a pensar que eso tiene una frecuencia muy baja. ¿Vale? Vale. Vamos a la rueda. En la rueda, tenemos la rueda dando vueltas. Ahí la rueda. Ahí. Me voy a fijar en uno de los radios de la rueda. ¿Vale? Y yo a lo largo del tiempo voy a apuntar dónde está ese palo de la rueda. Es solo ese. Me voy a fijar solamente en uno. Entonces digo, pues mira, en t igual a 0, por ejemplo, está aquí arriba. T igual a 0 está ahí. Luego miro un poco más para adelante. O sea, el palo de la rueda va a hacer así, ¿no? O sea, al principio voy a apuntar solamente su componente vertical. T igual a 0 hasta aquí, empieza a girar y va recorriendo. O sea, eso es lo que hace el palo de la rueda. Vale, es un seno, de hecho. Ya yo tomo muestras de esto. Si yo tomo muestras de esto y las tomo bien, muestras bien, ahí está. Si las tomo lo suficientemente rápido, yo veré que paro la rueda, primero está arriba, luego va para abajo, luego va para arriba otra vez. Pero si yo tomo el palo la rueda y tomo muestras más separadas, voy a tomar esta y voy a incumplir niquis, ¿vale? Entonces, niquis me diría que tenía que tomar la I, pero yo la voy a tomar aquí. La voy a tomar aquí. Estoy incumpliendo niquis con mucho. ¿Qué es lo que me parece? Lo que me parece es que estaba arriba y ahora está un poquito más arriba. Está arriba, pero lo que ha hecho ha sido dar una vuelta completa entre una muestra y la siguiente. Lo que ha hecho ha sido dar una vuelta completa y colocarse un poquito antes. Ahora está ahí. Y ahora tomo la siguiente muestra, que no sé dónde pilla, pero aquí es muy fácil ver. Lo que va a hacer va a ser dar una vuelta completa y yo voy a poner aquí. Entonces, una rueda que se está moviendo hacia acá, yo la veo como que se mueve hacia acá. De hecho, si tomo la muestra fatal, vamos a tomar la muestra fatal, así, pues yo tomo una muestra aquí y tomaré la siguiente justo en el siguiente periodo. Y la siguiente justo en el máximo del siguiente periodo. Con lo cual a mí me parece que la rueda está quieta. Eso también se ve en el vídeo. Pues esta es la rueda. No, que para eso hemos tenido que entender toda esta historia del SAM, del aliasing. Esta que se va moviendo hacia atrás, de hecho, a mí me parece que tiene una frecuencia muy baja. Si yo lo conecto los puntos rojos, a mí me parece que tiene una frecuencia bajísima. Que es justo el efecto que estamos viendo ahí. Y lo de para atrás, para que la rueda moviéndose a la izquierda o moviéndose hacia la derecha, porque hemos estado hablando de frecuencias todo el rato, pero eso piense bien. Que se mueva hacia la izquierda o se mueva hacia la derecha. La fase. Todos esos coeficientes, aquí hemos estado hablando todo el rato de sus amplitudes, pero también tienen fase. Bueno, pues la fase de esto será tal que parece que no se mueve hacia la izquierda o hacia la derecha. Muy bien. Más preguntas. No hay más preguntas. Me he hecho un favor, porque ya casi que he explicado el tema entero. Venga.
Yo no entiendo mucho, o sea, entiendo lo que quiere decir, pero la diapositiva en sí, la 21.
A ver. La 21. Esta.
Sí.
Muy bien. ¿Qué es lo que entiendes tú de...
O sea, entiendo eso, que aplicas un filtro para que no se produzca el aliasing.
Eso es.
Pero es que no entiendo eso de las H's.
Vale. Un filtro será una convolución con un kernel, ¿no?
Sí.
Pues este es el kernel. ¿Y qué valores concretos? ¿Esto qué? O sea, al final tienes que poner números. 0,1 menos 0,05. Todo esto al final tienes que darle el número. ¿Qué número pongo? Pues ya lo sabéis, la sync. Vamos a poner una sync. Depende del filtro que ponga. Si pongo este filtro, está en azul, entonces es una sync en X por una sync en Y. Si pongo este, es una función que se llama la hinc. Funciones de veces no habéis visto nunca, ¿no? Pues vamos con eso.
Depende que se ponga una u otra.
O de lo que tú quieras hacer.
Ah,
De lo que tú quieras hacer. O sea, downsampling puro necesitarías este solo. Esto es como el problema de esto, no, el problema o no el problema, es que en cada dirección tienes una frecuencia de corte distinta. O sea, aquí tengo una frecuencia de corte que es 1 partido 2n, en esta también, pero en la diagonal, por ejemplo, pues tengo 1 partido 2n por raíz de 2. Entonces, para cada dirección tengo una frecuencia de corte distinta. Si me quiero simplificar un poco la vida, pues pongo la misma frecuencia de corte para todos. Y eso computacionalmente pues, te da un poco igual, porque lo puedes hacer simple. La puedes, aquí en la H, o sea, lo único que cambia, que pongas esto, que pongas esto, es que los números son diferentes. Pero al ordenador le da igual, va a multiplicar por esos números lo que te ha dado. Si lo haces, toda esta cosa también se puede hacer de forma óptica. Entonces, tú puedes poner lente, hay formas de poner filtro anti-aliasing en las lentes. O sea, cuando tú pones una lente, la onda que llega, en algún punto, lo que tienes es la transformada de Fourier de esa señal. Entonces, en ese plano, yo puedo poner un disco y es mucho más fácil construir discos que construir cuadraditos. Entonces, construyo un disco y ahí pongo un círculo y estoy haciendo un filtro paso abajo. Vale. La función de Bessel. A ver. El seno y el coseno, todo el mundo lo conoce, ¿no? Y estáis acostumbrados y ya lo habéis interiorizado, pero en el fondo, y eso le pasa a cualquier función. O sea, cualquier función. ¿Qué es una función? Pues una función es una tabla. Es una tabla. Imaginaos que yo digo, pues esta es mi función, igual a f de x, y mi función está que al 0 le asigno el 0, al 0,5 le asigno el 1, al 0,75 le asigno el 1,5 y por aquí al menos 0,5 le asigno el menos 1 y al menos 1 le asigno el menos 2. Yo os doy, para todos los números reales, os doy cuál es la correspondencia. Dice, hombre, ya, pero claro, me puedes dar la tabla, ¿vale? Pero esta tabla es infinita. ¿No me puedes decir algo más fácil? Digo, sí, mira, 2x. Ya. O sea, ¿qué es una función? Una función simplemente, tú entras con x, entras con y, o sea, sales con y estás con 2x, pues para aquí. ¿Vale? Esta es la representación gráfica de todos estos números, pero ya está. Y esta expresión simplemente es una forma fácil y compacta de calcular eso. Vale, ya al seno nos hemos acostumbrado. Pues yo esto es igual al seno de x, no hemos acostumbrado y sabemos que estas cosas, así, no sé qué, pero sería x, sería y, pero es una tabla igual que esta. Bueno, pues hay otras funciones que ya no son tan fáciles, pero conceptualmente es lo mismo. Entonces, van las funciones de Bessel. Vamos a buscarla en inglés, seguro que está mejor. Pues las funciones de Bessel al final son las mismas cosas, o sea, son funciones. Lo que pasa es que además, funciones de Bessel hay de primera especie y de segunda especie. Dentro de las funciones de Bessel y luego están además las funciones modificadas de Bessel. Y bueno, pues hay como 500 derivadas, ¿no? Pero esto es como si me pongo un seno y ya está. Y ahora, ¿qué es lo que pasa? Por ejemplo, la función de Bessel de primera especie o la función de Bessel de primera especie está suma. Qué complicado. Pero si esto es lo mismo que una tabla, entonces, en vez de darte la tabla, pues, que antes te decía que era 2x, pues estoy dando la tabla, pero ahora te digo que es una expresión mucho más compleja. Pero es una función. ¿Y qué aspectos tienen esas funciones? Tienen este aspecto. Esta es la función de Bessel de primera especie y orden 0. La función de Bessel de primera especie y orden 1, y así. Porque aquí aparece una cosa que es la alfa, que es el orden de la función. Pero son funciones, además se parecen así, son de estilo seno, parecido a seno, ¿no? Vale. Bueno, pues, si yo ahora, aquí voy a poner Lec15. Voy a poner ¿Qué era la sin? La sin. O sea, a partir del seno, yo podría definir la sin. La sin, la C significa el seno cociente. Bueno, pues esto es seno de pi x partido por pi. Esta es mi definición del sin. Vale, pues ahora voy a definir la fin. La fin de x, yo no me la sé, yo no sé qué es. Eso está entendido. Pues es la función de bs de primera especie y orden 1. Tiene este aspecto y viene la fórmula aquí. Es la función de bs de primera especie y orden 1 partido por x. Depende de con quién hable, aquí pone un pi o no pone un pi. Vale, vamos a quitarle el pi para que se parezca a la definición que vamos a dar ahora. Pues esta es J1 de x partido por x. Bueno, pues todas las cosas que tengan este tipo de respuestas, esto es t, esto es t, esto es x de t. Pues cuando hago la transformada de Fourier de eso sí que lo sabéis. Lo que tengo es, vamos a coger el color de transformada de Fourier. Cuando hago la transformada de Fourier de eso, lo que tengo es así, alguna forma de omega. Tiene parámetros, pero no nos vamos a preocupar ahora mismo de esos parámetros. De omega. Tengo la sin. Cuando estoy en dos dimensiones, y tengo un disco, aquí X, y tengo un disco, este es el equivalente 2D de eso, ¿no? Vale, pues cuando hago su transformada de Fourier, ya no me sale, ahora tengo dos ejes, no, con el color de transformada de Fourier. Mi color de transformada de Fourier, ahora tengo omega x, omega y, y aquí lo que tengo es una phi. Cuando tienes simetrías radiales, las funciones que aplican ya no son los senos, sino son las funciones de Bessel de primera especie. Vale, en óptica aparecen muchas cosas. O sea, en óptica, como tú, lo que es fácil de construir, las lentes son redondas, los agujeros son redondos, todas las cosas en óptica suelen ser redondas. Pues lo que aparecen son funciones de Bessel. ¿Dónde que venir? El filtro este. Pues este va a ser el producto de dos signos, uno en X y otro en Y, mientras que este va a ser una función clínica. Y lo único que cambia de forma computacional son los numeritos. De hecho, la GIN y el producto de dos senos pues aparecen mucho. No son iguales, pero el aspecto visual es el mismo. Venga, más. ¿Hay más preguntas? Bueno, pues si no, preguntas de Dios, antes de pasar a explicar yo lo que quiero. ¿No? Bueno, pues si no, cuento yo lo que quiera. Vale. Interesting things here. So, first one is this is an operation that we have defined as decimation. So let's go to the whiteboard again. So let's go to the whiteboard. So I always write it in 2 dimensions. Let's do it in 2 dimensions, and then I will go to 1. Okay, so I have an image xi, and then from this image xi, I'm using a square brackets because it is a discrete image. So the space is discrete. So I will construct a new one. So my new one will be the previous one decimated by a factor d. So d, for instance, can be equal to. Okay. So what I'm doing is I'm taking this image and I'm taking, so originally the image I has all these colors, has all these pixels. Now this will be the image J. So the image J will take this one because this is the 0, 0. So the J at 0, 0 is I at 0, 0. So let's put, so this is 0, 1, 2, 3, this is 0, 1, 2, 3. So these two will coincide at this value. And then J of 1, 0. J of 1, 0 is I of 2, 0. So I'm taking this one. So what I'm doing is just taking one every 2 pixels in both directions. Okay, so and now my new picture, my new image will be just this one. Okay, this will be image J. That is simply copying these 4 pixels. Okay, this operation is called decimation. What is the, from now on, I will continue only in 1 minute, because otherwise all the expressions get too complicated. Okay, so let's say that we have a Fourier transform. So if I have a Fourier transform here, so I will have, I will continue with I, but now it is 1 minute. Okay, so I will have this Fourier transform. Well, this one. This one, Fourier transform of this is for, you may remember from 1D sequence. So it is 1 over d sum of k use d, small d, from 0 to d minus 1, of I d to the omega 2 pi d divided by. This is the part that I didn't want to write yesterday or a couple of days ago, just to not mess up with the different codes. But so d is, for instance, let's write it for d equal 2. So for d equal 2, we have this 1/2, and then I have 2 sums. So 1 is this one. And then the other one is this one. Start. Okay, now I will write it like this. This is the same. Okay, so and then we have to close bracket. Okay, so let's see what is this. Okay, so let's say that I has this spectrum. So I has this spectrum. Pi, 2 pi, this is omega, this is the spectrum of I. And then it goes, let's say, here. And let us say that we have to be careful of making sure that the spectrum is limited to pi-half. Okay, now we have 2 copies here. So let's do the 2 copies of different colors. So I will first draw this copy, and then I will also draw this copy. Okay, so what happens to this one? That one is the frequency axis is expanded by a factor 2. So that And there is another copy here. Okay, so here. And it also goes to minus infinity, okay? But I'm not drawing that. Okay, then let us do the Fourier transform of J. I will draw here now the Fourier transform of J. We'll make it very, very long. We will need to draw a few copies. So this is the Fourier transform of J. And the Fourier transform of J is made up of two copies. Okay, so let's see. So first one is this one. Okay, so that one was, I think, that one. Okay, so it is the same axis, but now expanded by a factor 2. So now it goes to pi rather than pi half. So before it was pi half, now it expands to pi. And this copy here at 2 pi, it will go to 4 pi. So I will have now here at 4 pi, I will also have another copy that goes to 3 pi on one side and to 5 pi on the other side. And then it repeats from minus infinity to infinity. Okay, but this is not a discrete signal. This is not the Fourier transform of a discrete signal, because it should be periodic with period 2 pi. So that is a copy that is missing 2 pi. So now this one is the same expanded, so the frequency axis is expanded, but it is shifted to 2 pi. So now this will fill these gaps at 2 pi, and then also at minus 2 pi. And again, it repeats. So now there's another copy there of this kind of red one. There's another copy here, and it goes from minus infinity to infinity. So the sum, this sum here, is accounting for filling the gaps. Okay, so because of the decimation by a factor d, the frequency axis is expanded by a factor d, but then I'm creating gaps, and then the gaps are filled by the sum. So that's a sum of shifted copies, shifted in frequency, shifted copies of the spectrum. Okay, so this is what will happen when this will happen when I do the decimation. The decimation is here. When I do the decimation. So at the end, I want to do a decimation, but this decimation is typically represented. So I have an image I. And then I want to do a decimation. But before doing the decimation, I have to make sure that the spectrum of I is limited to minus pi half, because otherwise I will have aliasing. Because then, when I do the expansion, this copy will invade my central copy between minus pi and pi. So I have to do the anti-aliasing filter before. So I have to do my anti-aliasing filter before. And this is the one that we have seen before. So we look at the spectrum, omega x, omega y. Either it is this one, and it goes to pi half minus pi half on this side, and then this side pi half minus pi half. Or I can say, no, I don't like this thing of having different cutoff frequencies in different directions. So I will just put pi half in all directions. This is using the same frequency notation that we have used in previous courses. The one that is used here of frequencies for that thing. Yeah. It is 1/20. So this is in. Okay. Another interesting idea. Why do I get copies when why do I get copies when I sample? So let's go back to here to the very beginning. So we have a continuous signal. Now we sample. Why do we get copies? Because this blue one, so this blue signal is, I can, let's forget for the moment that we have discrete and continuous signals. So discrete in the sense of x of n. So x of n is x of nts. Now this is continuous. Okay. So this one here is x of t multiplied by a set of deltas. So this function, this is the standard one. This is the signal you are sampling. This is x of t. This is t. But this one here, this one is a train of delta. So this is a delta, and delta, delta, delta. Everything is here. So this is pi ts t, and this is time. Okay, so and the separation is so I'll write it in this way. So let's say that this is 0, this is ts, this is 2ts, and it goes from minus infinity to infinity. So I can write this thing as the sum from k minus infinity to infinity delta pi minus k ts. Okay, so it is a train of deltas. And if I do the Fourier transform, and now we do the Fourier transform, this is the Fourier transform of this signal here. So let's call this signal, let's call it y of t. So what is the Fourier transform of y of t? So this is the Fourier transform of this one, or the Fourier transform of my train of deltas. I think it is time to make a break. Also, it's time to make a break. Let's make the break here before we put what is the Fourier transform of the train of deltas. Venga, 10 minutillos. Son 28 by 38. Okay, so let's continue. Okay, so we are here. So we have to convolve with the Fourier transform. So we have, in real space, it is a multiplication of two functions. So in Fourier space will be the convolution of those two Fourier transforms. Okay, so what is the Fourier transform? It's the Fourier transform of this one. So I will not write the expression, we will make a drawing. So yeah, even we can write the expression. Okay, so a train of deltas will be another train of deltas. So now the Fourier transform of x is pi. So pi ts j omega will be another train of deltas. And this train of deltas will be separated. This is my omega axis. Will be separated by ts. So if this 1 over ts. 1 over ts. And we are in radians, so 2 pi over ts. Okay, so the amplitude, I'm not sure about the amplitude, but I think it is 1 over ts. But we don't care about the scalar factor, so it will be, let's say that I'm right about 1 over ts. So it will be another train of deltas. And now, let's call this one omega s. So it will be the same as here. So it will be omega minus k omega s. So a train of deltas, the Fourier transform is another train of deltas. And how does it behave? So let's say that I make the sampling rate very small. If I make the sampling rate very small, the associated frequency will be very high because Ts is small. And if I make Ts very large, then the associated frequency will become smaller. Okay, so now I have to convolve this Fourier transform with this one. Now I can only draw. So let's say that the Fourier transform of this one. Let's say that this Fourier transform. I'll do it in a different color. So let's say this. So let's say that this Fourier transform is like this. So I can throw in just the amplitude. And this is omega, this is omega max, this is minus omega max. And it goes to 0 all the time, 0 all the time. Okay, now the Fourier transform of this will be, I have to convolve this one with that one. So it will be the convolution of these two. The convolution of those two will be the central copy. I'm convolving this function with this delta. Then I get this one. That goes from omega max to minus omega max. We have here 1 of this. Let's say that this is 1. And now I'm convolving this one with that one. So at omega s, I will have another copy. And this point will be omega s minus omega max. And this point will be omega s plus omega max. And again, it has an amplitude 1 over ts. And so on. So I have to convolve with all of those. Okay, so what will happen if my sampling rate is very large? If my sampling rate is large, omega s will be small. So omega s is small, that means that this copy moves here. The same happens from the other side. So we have another copy at minus omega s, and that one moves towards the center. So at some point, they may be very close, so close that they are touching each other. So at some point, I will have this one, same amplitude, but then the other one is touching the other. Okay, and then I have here omega s. When does that happen? That happens when omega max is equal to omega s minus omega max. What implies that omega s is twice omega max. This is Nyquist. So Nyquist tells you what is the maximum sampling rate that you can have. Beyond that sampling rate, you will have aliasing. These two copies will bump onto each other. And then there is a conversion now to discrete signals. So I have made all this reasoning with y of t. That I don't know what problem we live in. Let's say we have done all that reasoning with y of t. That was the product of x of t times the train of deltas. But now we will produce, so that was an intermediate signal. Now we will produce x of n. X of n is substituting the Dirac's deltas by Kroneker's deltas and changing the axis from time to samples. So when you do that transformation, what happens is that the Fourier space, this is again Fourier transform. Now the axis gets compressed. So now we have here. So it will be the same representation that you had before. So same representation. You will have this one here, another one there, but now the axes are different. So now the axis, this middle point here, this point in the middle, this point in the middle, let me see. This is omega s divided by 2. So omega s divided by 2 goes to pi, and omega s goes to pi. Now this location here is in pi. Okay, so this is when you make it discrete. Okay, so that comes to these drawings. So I have done all the drawings in one dimension because it is much simpler to do. But I can do the same reasoning, but now in frequency space. And this 1 over n is the number of samples. So his reasoning is all the time. This n is our d. Okay, so our capital D. This is the decimation factor. So the decimation factor also, think of these. So where are our decimation? So our decimation is somewhere here, and here it is. So the decimation is here. Yeah. So this. So our D there is his N. So this process, I can also model it as, so I can say Ij at a particular location, at some point, is this of xi multiplied by a train of deltas that are separated d. Okay, now, so it's a train of deltas that is separated d. So it is 1, 0, 1, 0, 1, 0, if d is equal to 2, and in both directions. So I will have the same kind of effects, but now with the discrete spectra. Okay, so that is what he's showing. Okay, so the train of deltas, the Fourier transform of the train of deltas with separation d will be separated 1 over d. Okay, so we will have a delta here, another delta, and his spectra. We have drawn all the spectra between minus pi and pi. So for us, the spectra was our spectra going to be blue. Okay, so we have drawn our spectra. Say this is the power spectrum of that signal. Again, in one dimension. And in one dimension, we have drawn it in this way. and it is a couple of deltas. So it is a train of deltas. So it will be a delta here, a delta there, a delta there, a delta there. And this separation is pi over 2 for us. For him, this axis. So this is the axis omega, this is omega. Okay, for him, and this is also very common for many other people. So the spectra, they use the same letters, okay? This is same. But it goes from -1 to 1. I don't want to. So the key is that their omega, it implies here pi omega. That is why it goes from -1 to 1. And then this happens at 1/2. Okay, so it's representing in this kind of frequency axis. Let's call it omega prime. So that you don't get confused. And there is another delta here, another delta here. So in the discrete domain, it is also a train of deltas. And the separation is 1 over d. Okay? It depends on how you express your axis. Okay, so this is the Fourier transform of the train of deltas. And now we are convolving these circles here at the omega max. Okay, so that is coming from the signal you are convolving. So if 1 over d is not separate enough, then you will have aliasing. Let's make. Okay, so let's say. So let's say that you have a signal. So let's do it in one dimension. Okay. So you have a signal. This is 2 pi, and this is pi over 3. Okay, minus pi over 3. And this is more. This is omega. And then I have here the same. So I do downsampling by factor 2. So I do a decimation by a factor, by a factor 2. What will happen to the spectrum? So the decimating, this point will go to 2 pi, over 3. But that is smaller than pi. So there is no aliasing. And this 2 pi goes to minus plus 2 pi minus 2 pi over 3. But again, this is larger than pi. Omega, and this is after the decimation. So let's say this is image. This is the image J. Okay, so depending on how is your spectrum originally, you may have aliasing or not. So that is what is being represented here. So you will be convolving with a new set of deltas. But depending on how large your omega maximum is, you may have aliasing. Yeah, this is this train of deltas. And the multiplication. This is explaining the whole process that I have explained in one dimension. Okay, so depending on how wide is your delta, this is the convolution of the spectrum of the delta. You may not have aliasing. So if you restrict your omega maximum to be restricted to the right frequency band. So I know the separation will be 1 over d. So if I make my filter to go up to 1 over 2 d, then I will not have aliasing. And here it is the aliasing as computed by the Fourier transform. So you may remember this is the same representation that we were doing So let's say I can give you two Fourier transforms. So the first Fourier transform, goes from -pi to pi, and that is when we have the frequency, the zero frequency in the middle. But I'm giving you the same information if I give you the Fourier transform between 0 and 2pi. So you might remember when we were explaining this, the Fourier transform, we had all this rearrangement of the different regions of the Fourier space that was given by the FFT shift. Remember? So the FFT shift is an operation that either gives you this or this one. Gives you one of the two. So if you are in one, you get the other. Okay, so if I put my frequency in the middle, my zero frequency in the middle, the aliasing comes from the high frequencies. If I rearrange my quarters of this Fourier transform, and I put the zero here, now this is what I see. Okay, so this is low frequency, this is low frequency, low and low frequency, and this is the high frequency. And this is the same when you don't have aliasing. So here it is when you have aliasing and you don't have aliasing. So let's look at, we normally prefer this kind of thinking. So if there is no aliasing, the region that is well preserved is this one, while this is the region that is contaminated by the high frequencies of the next copies. So that plot, this plot here, is the equivalent one I did before. I did one somewhere. This one here. This is the equivalent to this one. Okay, so the central, the low frequencies are preserved, while the high frequencies are contaminated. And
in the first image, you said that the ones that are far are the low frequency. In the first one.
First one is which one?
The first one.
Here?
Yes.
High frequency is here.
Because
This is 0, this is 2pi. So 0 and 2pi are low frequencies. Then this is pi. Pi is the high frequency. Okay, so then let's see how. So we understand we have to restrict our signal to a band region so that when I do the decimation, I don't have aliasing. So let's say I have that original image. I compute the power spectrum. So that goes from -pi to pi. And this will be my anti-aliasing filter. I black out everything outside. Then I can do the inverse Fourier transform. Okay, so this is the inverse Fourier transform of that. But then here I have ringing. I have ringing when I have step functions, and we understand this one. This is a low-pass filter. This is an ideal low-pass filter that we have already seen that it produces ringing. So, but now we know the trick. So I can use Gaussian filters as anti-aliasing. This will be my anti-aliasing filter, and I'm using here the sigmas in Fourier. The sigmas in Fourier space. Then that is the multiplication, and then this is the decimated image. And the decimated image, we don't have ringing anymore because we have used this Gaussian filter, but now it is a little bit blurry. And why it is blurry? Because we have filtered too much. So we have filtered all these regions, all these corners, they have been removed from the output Fourier transform. So, or removed, in the sense that they are multiplied by a very small number. Okay, so then and increase our Gaussian. So now our Gaussian will be larger. Will we have aliasing? Yes or no? We will have aliasing. Okay, because outside this square, no, things are not zero. But if we are happy to sacrifice that, then this is what we get. And now we get aliasing at high frequency. So this pattern here is not natural. This is not how the grid looks like, that region. Okay, but we don't have aliasing, but we don't have ringing. So here you have different comparisons. So that is the ideal filter. This is with the Gaussian that is blurring too much, but the grid is correct. We don't have aliasing. And if you increase the sigmas, now the aliasing. So the grid is not correct. And the aliasing happens at high frequency. So we don't see aliasing here. All these areas are very flat. You have to look at high frequency regions. And the grid is a high frequency region.
How do you know which one is better?
How do you know what?
Which filter is better?
It is a better for both. So when you define, and that is a very engineering thing. So when you define what is better, it is better with respect to something. So if it is with respect to having ringing, that one doesn't have ringing. If it is better with respect to frequency preservation, this one is better, even if there is ringing. But in the region that I have cropped, the frequency content is perfect. I have ringing in real space, but in frequency domain, it is perfect. But it is better with respect to what is your criterion. That normally, depending on your application, you may have different criteria. All there. And now you do the decimation, and then if you do the decimation without any anti-aliasing filter, you get the aliasing at high frequencies. In the trees you also get, but you don't see it because it is very randomized, and then we are not good to see it. But you also have this. Yeah, this is another of what is happening. So let us do this reason. What time is it? We have. Okay, so let's do this reasoning all together.
Decimation and downsampling are the same.
Decimation, no, downsampling is anti-aliasing and decimation. Decimation is just dropping one every 2 samples or one every 3 samples. So in this, that was drawing maybe somewhere. It was up here. Or was it here? So this is decimation. That's for it. This is decimation. All these is downsampling. Okay.
So the decimation is taking one of the samples.
One of D in my notation and in the slide. Actually, there is a very simple anti-aliasing filter, and that is sometimes it's called binning. Okay, so when the anti-aliasing filter is this one, I will put it in real space. So here it is in Fourier space, but in real space it's this one. When this is the anti-aliasing filter, this operation is called binning. And always be careful about words, because different people use words in different ways. So, but yeah. So there is a special case in which this one. What is the effect of this kernel on the image? It's computing the average of 4 pixels. Okay, so you take 4 pixels, compute the average. That is your main output. You go to the next, compute the average of 4 pixels. This is your output. So it is a very simple way of doing binning, but you are doing an anti-aliasing filter with this kernel that is very weak, in the sense that it drops very smoothly. So we have here a bit. So this Gaussian is letting a lot of aliasing outside. And the other one, the one of binning, is even more. Yeah.
When you do decimation, like they're reducing the number of pixels.
Yeah, decimation, you are reducing the number of pixels.
So the image is less sharp.
Is?
Like less sharp than the
Yeah, you are copying, you are just focusing on this area. So after the decimation, this is what will be left out. So you have lost all the high frequencies.
But why in the slide, I think it's more sharp?
It's not sharper. It's sharper, you think. That one?
No, the one that says decimation.
The one that says decimation. That one.
Yes.
Yeah, but here you have aliasing. So it is sharper, yeah, because of this sum. Let's say, what is it? It is because of the aliasing here. So in this area, we have aliasing. So at the output, so if I don't decompose into two signals. So I can use the same problem. So if I don't use the same signal, if I don't decompose it, what I will see is up to here I have some spectrum, but then I have the addition of two spectra. It will be like this. It will be more high frequencies when it is repeated. Goes every 2 pi. This is pi, this is omega, this is the decimated one that I don't know, this one. So it has more high frequency energy. So that is sharper. Okay, but it is artificial. Okay. All this explanation is about the foreplay. The overlapping patterns. Okay, so let's do it here on the right. Okay, so let's say that let's look for some free space. Okay, so I have some Fourier transform. Our Fourier transform. So this is my Fourier transform, and this is very well. This is also very well. Omega x, omega y, and then our Fourier transform. Let's say that this reading here, that I will decompose to 16 pieces, and I will let me try to use the same numbering as in the slides. With this 1, 2, 3, 4. 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10, we have copies of these. So we have the nearby copy. And the nearby copy will have the same information. And we repeat it like this. 4, and then 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. And here on this side the same, here on this side the same, here the same. So let us draw a few of the copies. I'm not putting the numbers anymore. We have another copy here. We have another copy here. Okay, because it is periodic. I'm not putting the numbers anymore. Okay, so now I will do the decimation. So from here to there, sorry. So it's maybe smaller so that you can see. So here we do the decimation. So we know that this copy will expand. This copy will also expand. And now I will draw it again between -5 and 5. Okay, so here our axes are blue. Our axes are blue. Megabytes of the new image, mega Y of the new image, and then I will have my frequency will expand. So my frequency will expand. That means that I will have these 4 corners. I will have 1, 2, 3, and 4 with this region will be multiplied by 2 because of the decimation. But this region will also be multiplied by 2 because of the decimation. So that means that here I will have a copy from 10 and 11 coming in. Because this one will also expand. And you can make the same analysis with all the other copies. And then this is the contamination pattern that you get. So you will get, I was discussing here, 1 and 4 and 10 and 11. But then 12 is coming from the top, 14 is coming from this copy. And then here it is the same. 13 is coming from the top, 15 is coming from this copy. And so you will get in the same quarter, you will have 4 different regions that are overlapping. This is the same idea as this plot. So this is another repetition of this idea. Is what? Okay, so we will have aliasing, and now we have number which regions are overlapping with which. And that is why before doing the decimation, you want to apply for an anti-aliasing filter because you want this one because they will overlap for sure. They will overlap. So what you want is that this copy here, where you have 16 regions, you have 1, 2, 3, and 4, but all this is black. All this is 0. Because after the decimation, they will overlap, for sure. For sure. So what you want is that the overlapping is 0. So you have 1, and then plus 0, plus 0, plus 0. So the anti-aliasing filter is making all these regions to 0. So that when they overlap, because the decimation will overlap for sure, you are adding zeros.
But you first apply the aliasing and then the decimation.
Yeah, but this is the reason why you want the anti-aliasing, because you want the overlapping to happen with zeros.
But the overlap occurs after.
The decimation, yeah. In the decimation, you have overlapping. But you will always have overlapping, but you want overlapping with zeros, not the overlapping with my spectrum.
But the downsampling and the decimation are different things, but both decrease the number of pixels.
No? The anti-aliasing doesn't decrease it.
No, the decimation and downsampling.
Yeah, because the downsampling implies a decimation. So the decimation is reducing by factor 2 or by factor d. And then downsampling is anti-aliasing plus decimation. So,
but it's not better to have the anti-aliasing before the decimation.
Yeah, you have to do that. That is
but
what
not after.
After everything is mixed, then you cannot decouple it. So it is like, let's say that I add a couple of numbers here because of the overlapping. Let's put it simple, okay? Here, because of the overlapping, you are adding two numbers. And then I tell you, okay, the addition of two numbers is 11. What are the two numbers? I don't know. There are many numbers that the addition is 11. So you have to do it before, so that you make sure that all the other numbers are 0. And I tell you, the addition of two numbers is 11, but all the numbers are 0 except 1. What is that number? Is 11. Okay. Because the 4 numbers that I'm collapsing onto the same place.
So the anti-aliasing, we only need to make the rest of the values 0.
Yeah. Okay, so any other question? Check if we can find another. We have seen the aliasing with images with the train, but let's see if we can find another one. Let's see. Yeah, here you have one, for instance. So this is an image, and this is the same image with aliasing. And the aliasing happens always at high frequencies. There is another example of aliasing. So you have a strange pattern that doesn't belong to there. Any other one? These are examples with anti-aliasing, but we don't see the aliasing one. Yeah, here we have, for instance, this is with aliasing, this is without aliasing.
So it's not really optimized to first it's not very optimized to first
That after, no, you are making them 0 while they're 0. But you want them to be 0 because otherwise decimation will add non-zero values. Okay, more.
And what is the purpose of doing an image with these
Pixels. You may remember from the one from the presentation of edge enhancing that really you have a spectra that are like this. So you have your ideal image. This is the ideal. This is the omega. This is omega. Let's say this is pi, the model, and then your spectrum, let's say it is like this. It is very narrow. But then you have noise. Noise will be so you have also noise. And the noise is like this. So you have a little bit of signal, you have a region where you have more signal than noise, but then you have a lot of regions where you have a lot of noise. That is a lot of noise in your image. Why do you need such high pixel size, or such a high pixel, such a small pixel size, high sampling rate? If most of it is noise, what you can do is downsample. And then if I downsample, in the downsample one, this will expand. I have filtered this out. So let's say I do a downsampling by a factor of 3. So this is my pi/3. Now this pi/3, my new spectrum, you go almost to pi. You also go almost to pi. And then we have a little bit of noise. We have noise all the time, but much less than I had before. Here I had a lot of noise. Here I have a little bit of noise, and the region in which I have more noise than signal, but much less noise than I had before.
But we say that we can remove the noise applying
A filter.
a Gaussian filter, no?
Yeah, you can. Yeah, if you apply a Gaussian filter, I would repeat the same problem. So now our filter was blue, so let's say this is my Gaussian filter. So then I would have a little bit of noise now in this area, and then it goes to 0. But then still this is pi/3. This is pi/3. So in terms of information, all these components are 0. All these are 0. So in terms of information, I have the same information here as in there. Same information. How many pixels I have here? 9 times more. So I have same information, but it occupies 9 times more pixels. So why occupy more space?
And this is what?
Can you repeat that?
Yeah. So in terms of information, I have the same information here as in there. I have not lost. Let's say that the filters are the same. So I have not lost any information. I have preserved all my information. Here, it has been multiplied by zeros. I have a lot of zeros in my frequency space, but then that means that I need, because of the downsampling is d, but d in each direction. So I have d squared fewer pixels in this image than in there. So why, for having the same amount of information, why having more numbers? I can have d squared times fewer numbers.
So
You see the amount of pixels in the y axis.
This is
The amount of pixels in the
y and x.
in the y axis.
The total number of pixels is d squared times less. So it is d times less in one direction, d times less in the other direction, and then in total it is d squared. And I have not lost information. Information content is the same.
So both do the same thing, but it is better to apply the downsampling because of the amount of pixels.